Hey everyone, and welcome to This Explainer. Today we're going to put on our mathematical X-ray glasses to totally deconstruct the exact geometric building blocks that make up the physical world you interact with every single day. You know, we often move through our environments without giving a second thought to the hidden architecture holding everything together. But today, we're going to change how you see your surroundings entirely. All right, let's dive right in.
Here is the roadmap for our journey. First, the 3D world around us. Then, faces, edges, and vertices, followed by down to one dimension. After that, we'll look at the angle of things. And finally, flat shapes and polygons.
Let's kick things off with Section 1, the 3D world around us.
Think about the tangible stuff right in front of you. A suitcase you'd pack for a trip, a heavy textbook you're studying from, or maybe just a simple juice box from the fridge. Our brains naturally process these as distinct, functional objects. But geometrically, everyday items are elegantly categorized into specific solid shapes. A Rubik's Cube, a piece of chalk, or a die used in a board game, these are perfect examples of what we call a cube. On the other hand, an elongated object, like that textbook or that suitcase, falls into a totally different category, known as a cuboid.
So what's the actual difference holding these physical realities together? Well, it all comes down to their surfaces. A cube is a shape built strictly of perfectly equal squares. Every single side is absolutely identical. A cuboid, however, stretches out. It's built with rectangular surfaces, meaning only the opposite sides match up in equal size. It's a simple distinction for sure, but it dictates the entire physical form of the object.
Moving right along to Section 2, faces, edges, and vertices.
Now that we recognize the overarching 3D shapes, our cubes and cuboids, let's get out our mathematical scalpels. We're going to dissect these 3D solid objects to see the specific anatomical parts that hold them together. The very first piece of anatomy is the face. The flat, smooth parts of an object that you can literally run your hand across, like the front cover of your math book or the side of a tea box, are defined mathematically as faces. They are the closed, plane surfaces that form the boundary of the solid object.
But a face doesn't just go on forever, right? It eventually ends. When two of those flat, plane faces crash into each other, they form a distinct, straight boundary line. In the mathematical anatomy of an object, this joint where two surfaces meet is known as an edge.
And the deconstruction goes one step further. If you trace your finger along those straight edges to the exact pointy corner where multiple edges intersect and terminate, well, you've found a vertex. These are the sharp joints tying the edges and, consequently, the faces all together.
When we strip away the solid exterior to reveal the raw mathematical skeleton, you can literally see the invisible math holding a cuboid together. A flat plane, say defined by points A, B, C, and D, acts as a face. The single line connecting A to B is an edge, and that solitary corner point A, that's your vertex. It's literally the scaffolding of reality.
To truly cement this idea, the source text outlines a brilliant physical exercise to prove this structural anatomy. You can actually build your own hollow 3D model right at your desk. You just use simple juice or wheat straws to act as the edges. Then, you connect them at the joints to form the vertices. Finally, you paste distinct colored paper over the empty gaps to create the flat faces. It's a perfect physical manifestation of geometric theory.
Which brings us to Section 3, down to one dimension.
But what happens if we take that physical straw model and completely destroy it? If we strip away the colored paper faces and break apart the straw corners, we leave the 3D world behind completely. We drop all the way down to a single dimension, exposing pure line segments. A line segment simply connects point A to point B. It has no depth, no height, just a length that we can measure in exact units, like 5, 7, or 10 centimeters.
These one-dimensional lines are the absolute fundamental scaffolding of everything we've talked about so far. Think about it for a second. Without these individual line segments, there are absolutely no edges. And without edges to border the faces, those 3D cubes and cuboids simply collapse into thin air. Reality starts with the line. Let's step into Section 4, the angle of things.
Of course, in the real world, lines rarely exist in perfect parallel isolation. They eventually cross paths, and the mathematics of that exact collision is crucial to giving our world shape and structure. When two line segments cross paths and intersect at a vertex point, the gap created between them is called an angle. We meticulously measure this gap using a protractor in precise degrees, ranging anywhere from a sharp 30 degrees all the way up to a wide 150 degrees.
And studying these shapes reveals a fascinating, unbreakable, hidden rule of geometry.
When measuring triangles, the source material highlights an amazing relationship. The longest side of a triangle is always situated directly opposite its greatest angle. And conversely, the smallest angle will always face the smallest side. The lines and angles are in constant, predictable communication with each other.
Finally, we arrive at Section 5, Flat Shapes and Polygons.
Once we lock multiple intersecting lines and their distinct angles together on a flat plane, we step up from the one-dimensional world and enter the two-dimensional world of flat shapes, also known as polygons. To test how well we can visualize this translation from lines to shapes, the source poses a really fun riddle. What flat shape are you if you have exactly 4 sides, it's a closed plane figure, and every single one of your internal angles is perfectly equal?
So looking at the multiple choice options provided in the text, a triangle, a rectangle, a generalized quadrilateral, or a circle, the exact correct answer is a rectangle. It's a highly specific type of quadrilateral where all 4 intersecting angles measure exactly the same. Let's see how this builds out into a much larger system.
Synthesizing the mixed exercises from the source, we can systematically map out these flat shapes. Triangles are mathematically locked in with exactly 3 sides. Quadrilaterals step up to 4 sides, and a pentagon expands out even further to feature 5 interconnected line segments. Each polygon is simply a different configuration of 1D lines and angles enclosing a 2D space.
What's really vital to grasp here is that these flat, two-dimensional shapes, these triangles and quadrilaterals, are the exact same concepts we used as colored paper to form the faces on our 3D straw models back at the very beginning of our deconstruction.
So the grand mathematical takeaway from all of this is that reality is basically just stacked lines and angles. By combining one-dimensional lines and the specific angles between them, we build two-dimensional polygon faces. Those flat faces then box together perfectly at sharp vertices to create the heavy, three-dimensional solid objects you carry around and interact with every single day. It is a beautiful, upward cascade of dimensions.
As we wrap up this explainer, I want you to apply this immediately. Scan the room you're sitting in right now. Pick an object. Looking through your newly acquired geometric X-ray glasses, ask yourself, can you break down the furniture around you into its pure anatomical faces, edges, and vertices? Once you start seeing the lines, I promise you'll never look at a simple, solid object the same way again. Thanks so much for joining me on this deep dive into the geometry of reality.